when I was looking up Center for Artificial Intelligence in Society, one of the first things that struck me is that it's a group of Department of Computer Science working with the Department of Social Work. In my knowledge, you can't get computer science to work with computer engineering. And so this is really interesting that there is an interdisciplinary effort in University of Southern California, that there is a vision to understand that this kind of work happens when we work together. We have today three folks who will be presenting, Milind, Eric Rice, and Bistra Dilkina, but we also have Jordan Davis and Phoebe Vianos, who are also faculty at CSUN and Brian as well. I'm sorry.
Well, thank you. This is so exciting. We've been working on trying to put this together in collaboration with Microsoft Research, and it's absolutely fantastic that this has come together. We are very excited. My name is Milind Tambe, and along with me here, as was just mentioned, we have Eric Rice and Bistra Dilkina, who will jointly give this presentation. And I should start my clock because I want to be done in 10 minutes, and then Eric and Bistra will take over and they'll speak for 10 minutes each. Phoebe, Vianos, Z, and Jordan, and Brian Wilder is our student. So together, this represents bulk of the center's faculty. So just to very quickly tell you about our center, we are this USC Center for AI in Society, or CASE. It's an interdisciplinary center. There's 6 key faculty who are all present here today. There's 24 PhD students. We only got 1 here, but the remaining ones are back there, and we'll talk to them later. Our focus is AI for societal problems, and we are very keen on starting projects in India. And to show our keenness, I wanted to show you 2 slides, no politics. So we were very thrilled to be in the audience when Honorable Prime Minister talked about AI for societal benefits in Mumbai, and so very inspiring. And then this was in February, and then in June, the Honorable External Affairs Minister held a roundtable meeting on artificial intelligence. And there too, we were honored to be invited, and that's me, you can see hiding behind in the back. But this is, again, we talked about how AI could be used for societal benefits. So we are very keen on starting projects here. And just to give you a flavor for the kinds of projects that we have done at USC, our focus has been on 3 areas: public safety and security, public health, and conservation. And I'll give a general overview, and then Eric will talk in depth about public health, and Bistra about conservation. So the basic problem we focus on is how to optimize our limited intervention resources using AI in order to solve societal problems. So let's take public health. Eric will discuss this in more depth, but give you a concrete example. HIV/AIDS is a big problem with the homeless population in Los Angeles. How to spread information about HIV amongst the homeless youth. We can't talk to everybody. There's 6,000 homeless youth. And so we have to identify key peer leaders who will spread information. We show that AI techniques are far more effective in finding these peer leaders to spread information compared to traditional methods. And this we have done with pilot tests on the ground. So these are always things that we test out. But can we try this out for TB prevention and for other kinds of health challenges? For conservation, we've been working a lot in Uganda for the past several years with the Uganda Wildlife Authority to protect endangered wildlife. Here, with machine learning, we predict where poachers will attack with traps or snares and remove them before they kill animals. We've done this for past several years. A lot of snares have been removed. Animals hopefully have been saved. And with drones, getting infrared video, detecting poachers and animals on the fly from these infrared videos so that they can be stopped. Bistra will discuss this in much more depth. We have also a lot of interest in public safety and security, counterterrorism. We've worked a lot with government agencies, Coast Guard, the Transportation Security Administration, large number of targets to protect, where and when to patrol, where and when to put security checkpoints and so forth. This is not the focus of this workshop. I'm not going to talk about it. But this is software that's actually in use for over a decade by these agencies, just to tell you that we are very interested in getting this software deployed and in use. This is now spreading to other countries like Israel and Argentina and so forth. So I wanted to talk a little bit about the fact when we solve problems, we firmly believe in interdisciplinary partnerships. So to that end, we've really worked with the Coast Guard, patrolling with them on their Coast Guard boats in New York, or patrolled in the forests of Malaysia with the wildlife conservation agencies. Eric has spent 15 years working with homeless populations in Los Angeles, and so on. So when we start solving problems, we always start with immersing ourselves in the domain and trying to get data. This is not a situation where data is ready-made available. We are very interested in trying to identify, get the right kind of data. Following that, of course, the next step is predictive analytics. That is, given the data, can we predict which cases may be high risk, which may be low risk? Many AI systems stop there, just predicting high and low risk cases. But we at our center are interested in doing more. We have limited intervention resources. Can we go beyond and do prescriptive analytics? That is, where to take our limited resources and place them so that we get the highest benefit, not just identify high and low risk, but which cases should we take on given our limited resources? Now, many AI systems will stop there. But our center, we really are very interested in going one step beyond and testing this prescription in the field and understanding where we have gone right and wrong so that this can then inform our data collection. Very quickly, just as an example, in the wildlife conservation domain, data collection would be where are the snares placed. Based on that, predictive analytics would say where are the high-risk areas in the park, where are the low-risk areas in the park. Prescriptive analytics would say where should you patrol given that you know high and low-risk areas. And finally, testing in the field would say, send out the patrollers, get them to patrol, do we get the results that we want or not? And if we don't, then change our model or algorithm. So as I said, all of the cases that I talked about are deployed, tested. We are very interested in actually testing things in the field and not just writing papers. And so this is very, very important to our center. I just wanted to talk about a few projects that we have in my last 4 minutes or so that may inform you about some of the ongoing efforts at our center. Eric and Bisra will talk more, of course. So for example, AI can help in obesity prevention efforts. This is an idea of how could we optimize public outreach efforts within limited budgets. Can we help improve TB treatment by predicting defaulters? And I understand Amit may discuss some of the work that's going on in this context. But let me take on this childhood obesity prevention. So this is in the United States a very large problem, childhood obesity. And so in the Antelope Valley, which is north of Los Angeles, where our university is located, there's a low-resource community where only 10% of the kids are perceived by their parents to be healthy. And so we are working with our School of Medicine to try to see if we can prevent childhood obesity. So this is done because the basic idea is trying to get peers to influence parents to get children to eat healthy. In other words, get mothers to cook together healthy food, but which mother should cook together? Because that's the way we'll determine health outcomes. And so essentially, if you look at it from a graph, each of these nodes you could imagine is a mother. The red node is the mother whose children are unhealthy. So who do we pair this mother with in order to get the kinds of health outcomes we want? So should we get this one to connect with this one and then maybe drop a connection to this other one because that's not an unhealthy relationship, or form this kind of a group, and so forth. So those are the kinds of questions we can solve. This is work that's going on in Antelope Valley. This is something that we're very interested in deploying. Another project that's also ongoing is work in Urban Peak. This is in Denver, a homeless shelter. Here we have a social network of youth who are addicted, who abuse substances. These are shown by the red nodes. The black nodes are ones who are healthy. And the question then becomes, can we create groups so that we reduce substance abuse? And so can we partition the graph, creating groups where healthy outcome prevails because the peers can influence this red node because they have been cut off from this other red node in order to change their behavior. So these kinds of things, trying to figure out which kinds of partitions can perform better so that we avoid deviancy training, because if you incorrectly create partitions, then actually addiction increases. So we want to reduce the addiction by creating the right kinds of partitions. A third challenge that we've recently taken on is trying to look at infectious diseases. In India, we know there's 500,000 deaths due to TB. How to get more patients into treatment. So there's an outreach effort, and some of you may know a whole lot more about this, but this is what we understand, that there are different outreach efforts. The question is, these different outreach efforts may reach different segments of the population, different geographical areas. who to target, how to spread our limited budget. And so we've constructed a multi-agent model for disease spread and an AI algorithm that, based on realistic data, can do an experimental evaluation. Based on this, we show that our models can do better than what has been done as status quo. Now, clearly, this is done as a simulation exercise based on realistic data that we can get hold of. But the basic point is, if we have limited resources, how to invest them in order to kind of get the right kinds of outcomes based on whatever data we have. So that's the type of work that we can do. So I'll end here by saying there is a tremendous potential for use of AI for societal benefits. We are very interested in applications here. We worked in Africa, in South America, and we are really keen on pushing this forward. So it's 10 minutes, and I'm going to hand this over to Eric to start his 10 minutes.
I'm really excited to be here as well. This is my opportunity to talk about two projects that are really near and dear to my heart, which are working with homeless teenagers. So I've been working with homeless teenagers and young adults for the last 15 years in Los Angeles. And I'm going to talk about one project that's on HIV prevention and another project that's on housing. And the point of this is really to give especially the folks who are in the NGO space in this room, a sense of how we approach our work and also some of the kinds of problems that we can tackle with technologies that maybe are things that you haven't thought about before. So the first thing that I want to mention, and Jordan Davis here is with me as well from the School of Social Work, is that social work researchers, we're very invested in very intimate partnerships with non-government organizations and government organizations. So Jordan and I have actually both done intervention work, small group work with, in his case, youth who've been in substance abuse treatment programs, in my case with homeless teenagers. And so we don't just do research work, but we actually do work out in the world that social service providers do. We do it hand in hand with them. So this is actually a picture of me actually interacting with a young person out in the field. This is something that happens on a regular basis. The issue is that there are 4.2 million homeless youth in the United States each year. There's 300 million citizens of the United States. We are not nearly as large as you all are, but homelessness is a big problem. What this has suggested recently is that almost 1 in 10 teenagers between the ages of 13 and 24 will experience homelessness every year. So this is becoming an increasingly large problem as the class divide becomes larger in the United States. HIV prevalence is nearly 10% amongst this group of people. So we really need to think about how can we target this very large group of people who need HIV prevention work. So our community partners in this context are 3 different drop-in centers where homeless youth can go and access services. One is a Safe Place for Youth, another is My Friend's Place, another is the Los Angeles LGBT Center, where we've done this work. These are partner organizations that I've been working with for about 15 years. And what we're trying to do in this context is a peer-led intervention. So the idea is we don't have enough resources to do HIV prevention work with every single homeless youth in the city. But we can find strategic folks who are the right people who can be our advocates, who we can train to go and do health outreach work in their community. The complexity of this, however, is that the social networks of these homeless youth, even within one of these centers, are these dizzying arrays. So what we're stuck with is a problem that I like to think of as very akin to the problem that Google Maps solves. So we're trying to do optimal planning. And what we have is a network where there's a lot of noise, there's a lot of uncertainty. We might not know exactly who's connected to whom. People might get into fights with one another and stop being friends with one another. So this is a moving target, much like traffic in a city is a moving target. But like with Google Maps, where you want a specific solution, we want a specific solution to who should we pick as this small group of young people that we can train to do this activity. So we developed algorithms that parse the community into smaller sections, find specific key leaders. I'm going to spare you all of the math, just show you pictures today. And what's exciting about this is that when we compare these systems to the standard ways in which public health and social work have done this in the past, what we see here is that the AI-driven solutions far outperform the usual status quo public health solutions. we're looking at, in these networks, we were seeing about 70% of the target youth were getting messages about HIV prevention versus only about 27% in the standard group. And then when we were thinking about people going out and getting HIV testing, which is one of the important things you need to do if you're going to link people into antiretroviral drugs, is that we see, again, a big difference here in terms of those who were reached by our messaging. We had about almost 30 to 40% of those young people went and got an HIV test, and so therefore could start to get engaged in treatment if they needed it, versus the standard public health arm of this field deployment, where we actually had no new testers in that space. So we see this not as a perfect solution, but when Milind was putting out this pathway of going from collecting data with community partners, then doing predictive analytics, and then doing prescriptive analytics, and then doing field tests, this is one example of a project that we've been invested in for several years, and we're actually currently right now just about to finish out a trial where we've enrolled nearly 1,000 homeless young people over the last year and a half into this program. And one last thing that I'll mention is that what seems to be of great benefit of some of these AI programs is that in an age in which especially young people are very excited about technology, these are two young men who were picked by our algorithms to become peer leaders, and they felt very empowered by this entire experience, and they actually started to do much better, and actually both of these young men ended up getting jobs and in housing within about within the 2 years after this initial program went forward. So the other program that I want to talk about is a little bit earlier in its development. This is something that I've been working very closely with Phoebe Vianos, who's not going to get a chance to stand up and speak, but I'm going to get to actually speak for her, which is not entirely fair. But here we're working on housing. So I've been working with organizations, governmental organizations and non-governmental organizations in the United States around housing issues for the last 5 or 6 years. This has been something that's a relatively more recent body of my work. But again, the issue is one of scarcity. So we have this huge number of young people who are on the streets, and we don't have nearly enough resources to give them. The United States is this very wealthy country with a very broken social welfare system. So we are working with the Los Angeles Housing Service Authority. This is the group, a governmental organization in Los Angeles that is both the city and the county in which we're located, and they provide most of the housing resources for homeless youth. And so they're our partner in this particular effort. And what we're trying to do here is something that is very much like Uber. So what the idea is that we have a small number of houses that are available at any one time. We've got a large number of people that are waiting for housing. So how do we match, just like Uber would match drivers to riders through this traffic, how do we match the right people to the right housing resources so that we can do two things? We can optimize the success of those housing resources, because since there's so few, we don't want to waste any precious resource. But the other idea is that we want to make sure that people are treated fairly. So there's a lot of discussion right now in the ethical area of AI around bias in algorithms, and that if you just train systems that are built on former data sets that may have a lot of implicit bias in them, you will just reproduce these biases. So what we really want to do in this is we want to improve on two things, fairness as well as the actual efficiency. So the current system for housing allocation is very simplistic. What you get is young people are asked about 50 questions, and from these 50 questions, they're assigned a score that ranges from 1 to 17. And depending on whether they score 8 or higher, they get really good services. If they score 4 to 7, they get rental subsidies. And if they score less than 4, they get nothing. We've approached this in the way that Milind described, and I guess this is not showing up so well. So this says machine learning about prediction, and then this is going to be policies that are prescriptive. But what we really want to do with these policies is we want to make sure that they're interpretable, right? This simplistic scoring mechanism, although it's maybe not the most effective thing in the world, which I'll show you in a minute, it at least is something that people can understand. So we want to make sure that the AI that we build in these social service contexts is one wherein people can explain to their clients that they're working with why they are or are not eligible for services. We can't just deny people housing and say, well, the computer says you don't get housing. So what we're interested in is optimizing our success like Uber, but we also want to make sure that we avoid discrimination. One of the big issues in the United States is racial discrimination. So these are Hispanic and Black youth. These are traditionally populations that have suffered a lot of discrimination and marginalization in the United States. I want you to just only focus in on the top and the bottom here. I don't have enough time to explain everything in between, but the top is the current system as it exists. And what you see here is the white youth that are purple, they're benefiting at much higher rates than the Hispanic and the Black youth. Phoebe's algorithm is able to change this. So this is a computational experiment where we're doing some prescriptive analytics, and we're saying if we changed who we gave the housing interventions to, so we didn't just do this simplistic system that is currently in place, we could greatly reduce, by looking at the individual characteristics of these young people, we could greatly reduce the inequalities here. And what's even more exciting, again, focus on the top and the bottom, is that you can see this is the overall successful number of outcomes in the system as a whole. And what we're able to do is we're able to create a bump of about 10% in this system, which is actually a really big deal. This ends up being thousands of people when you're talking about the scale of homelessness that you have in Los Angeles, where we've got 50,000 people on the streets on any given night. So with that, I will turn things over to Bistra, who's also going to talk to you about some of the implications that we've had recently.
CASE also has a lot of projects that involve using AI for wildlife conservation. As you all know, there's been a dramatic decline in the populations of many species, many of them endangered, like tigers and elephants, as well as rhinos and giraffes. Unfortunately, a lot of this decline is also due to poaching for illegal wildlife trade. So CASE, over the last 4 to 5 years, has actually partnered with several NGOs, such as WCS, WWF, and Pantera, to try to help them to develop AI-based tools to make the anti-poaching efforts more effective. And in the process, we have developed a tool called PAWS that helps them deploy patrolling efforts in protected areas to catch poachers in the act. In fact, PAWS, as I will show you later, has become so successful that now, in the last 5 months, we have partnered with SMART, which is a consortium which includes these 3 organizations as well as many more. And SMART has a tool which helps many protected areas record their data in terms of patrolling effort and detected illegal activity, and build reports for those protected areas. Now, SMART is trying to incorporate our AI-based tools to actually provide them analytics and planning component that will let them have more effective deployment in the field, and therefore will allow us to reach more than 600 parks in which SMART is currently used over more than 55 countries. So the way that PAWS works is actually, again, as Emilian mentioned earlier, starting from raw data collected over the years in these parks that includes the patrolling as well as the detections of illegal activity, combining it with additional information such as GIS information across the park on roads, rivers, the park boundaries, land cover, etc., and using that data to build a predictive model of where we expect there to be the highest risk of poaching, given the particular time of the year and the particular characteristics of a grid cell in the park. Okay, and together with this predictive model, then we are actually able to help them also with the prescriptive part, saying with the limited resources of park rangers that they have, where should they send them at any particular time. And so this is combining things like machine learning together with optimization and game theory. So as I mentioned, we have worked on this over an extended period of time. In particular, we have worked closely with 2 parks in Uganda, Queen Elizabeth and Murchison Falls. And so using historic data from those 2 parks, we have developed progressively more and more accurate machine learning models for the poaching risk, achieving accuracy of 0.86 in our best current model. But we don't stop there, okay? That's our accuracy in the lab. The most important thing is to actually see whether these models really work in the field. And so we went a step further and actually had field tests in both parts over between 6 and 9 months, where we generated patrol areas where they had not previously patrolled, some of which areas were predicted to be high risk and some low risk based on our models. And later in Murchison Falls, refined that to even high, medium, and low risk, without telling the rangers which is which. They patrolled from 6 to 9 months, and at the end of the day, we just looked at the data of what happened. And what we discovered that, in fact, the areas where our model was predicting high risk, they were able to find many more snares per patrol effort that they spent there. So in fact, it was extremely accurate in allocating resources more effectively than just guessing at random. So with this predictive model in hand, now that we also know it works in the field, we're also able to tell them more strategically of how exactly to send their rangers to patrol and incorporate important on-the-ground constraints, such as where are the rangers, where should they start from, how much can they walk at most in any given day. Right? And so with the predictive model and in these constraints, our optimization game theoretic model is able to generate maps like that, which says exactly where to walk and how much effort to spend in each grid cell, depending on the characteristics of that cell and the corresponding prediction of how likely they are to detect poaching activity there. So we are really excited about, in fact, going to the deployment stage, working with SMART, and really getting this system out in the world. In addition to rangers, an additional resource that more and more protected areas are thinking about using is the use of UAVs in order to augment the patrolling of humans. NGO with which we are working on this, called Air Shepherd, which is using UAVs driven in vans during the night and sending those drones to actually patrol in real time for poachers, and having people sit and trying to look at the videos in real time to detect poachers, call the rangers if something is suspicious, and respond effectively. Unfortunately, looking at these videos is extremely difficult and tiring, and so their current setup is not really scalable, so they came to us in trying to help them to build a more effective system. So as you can see, these black and white videos during the night with an infrared camera are extremely difficult to interpret. They are very low resolutions. The objects we are trying to detect are extremely small. The camera is moving. There's other things like vegetation and reflection that look exactly like the little specks that might be poachers, right? So it's extremely hard problem. So we built a system based on deep learning, which somehow the slides are all messed up. A system based on deep learning to predict, to interpret these videos. Unfortunately, labeling the videos is extremely time-consuming, and so we have a limited amount of training data. But we partnered with Microsoft and their a video engine called AirSim to actually create a version of it which simulates the African savanna and poachers and animals in that African savanna. And so we're able to, together with also a model of a drone flying in this simulation, to generate additional simulation data that looks very much like the real data. So together with the labeled very non-cost-effective labeled real-world data with augmented simulated data, we're able to, no, I guess it's not going to show the results on this side, to improve the accuracy of our model, both in recall and precision, much beyond their current system that they're using in the field. And so they're actually currently testing it, using it in their actual vans, and we also have a cloud-based implementation of this system. So beyond anti-poaching efforts, we also have several projects related to conservation planning and informing decision-making makers in how to most effectively use very limited dollars allocated to conservation to generate the best ecological impact. So one such project is, one such problem we know how to address is how to inform preserving landscape connectivity for species. So as the habitat gets more and more fragmented because of roads, urbanization, agriculture, etc., essentially species cannot move from one remnant of habitat to another, which really jeopardizes their long-term persistence. So what we can do about this is that we can try to selectively try to intervene, but by, for example, building overpasses over roads or underpasses, or protecting specific areas from urbanization, and essentially providing wildlife corridors for these animals to move and preserve their populations. However, this is a very difficult problem where you have multiple opportunities with different effects and different costs, which interact with each other, because essentially the combination of all these interventions change the landscape in terms of the best movement pathways for these animals. So we've developed an algorithm that allows for us to produce such intervention optimum plans. And so we've tested this in western Montana, where a threatened species called the wolverine has several remaining populations in the green parts, but which are basically disconnected because of high urbanization in the remaining areas. And the cost of intervention is also very expensive across most of the landscape. So with our method, we are able to generate a subset of specific intervention points here in red, which essentially reroute and improve the movement corridors for these species from the yellow ones to the black ones that are shown here, and help, hopefully, the long-term persistence of these species. So this was a brief overview, but this basically just gives you a sample of the kind of methodologies that we use in the conservation space, again, leveraging machine learning as well as optimization and game theory to help these NGOs. So thank you very much.